31, we have a couple piecewise functions here made by line segments, and ultimately the question tells us that h is defined as f divided by g, and we want to know what is h prime at 3. So ultimately, if we want to know h prime at any number, we need to find h prime first. So what rule is this issue about? Quotient rule. So bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. Alright, and we want h prime at 3 here, so we're going to need to figure out what's g of 3, what's f prime at 3, what's f of 3, g prime at 3, and g at 3 all squared. So let's see if we can fill in some blanks here. How about g of 3? Look at that g function. Looks like it goes through the point 3, 3. The f prime at 3 is the derivative of f at 3, and since it's a line segment, we can find its derivative because that's just a slope. So if we go from one point to the other, say we go from negative 3, 3 over to 6, 0, we go down 3 and over 9. So down 3 and over 9 would be a slope of negative 1/3. From the f function, if we go from essentially where it starts decreasing to the end, from negative 3, 3 to 6, 0. We go down 3 and over 9. And then f of 3 appears to be 1. And g prime at 3, g's derivative here, the slope, if we go from negative 1 up to, let's say, 5, 5, looks like it goes up 1, 2, 3, 4, 5, 6, and then over 1, 2, 3, 4, 5, 6. So slope would just be 1. And on the bottom, g of 3 we already said was 3. We'd have 3 squared on the bottom. So ultimately we'd have on the top, we'd have negative 1 minus 1. So we'd have negative 2 on top, 9 on the bottom. And negative 2/9 corresponds with letter A, like I said. Alright. Questions on any part of number 31? Next. 31, 35. 32, we have a region that's bounded by the x-axis and the part of the graph of cosine x between 0 and pi over 2. It's divided into two regions by the line x equals c. And if it says that the region between 0 and c is equal to the area of the region between c and pi over 2, then c must be what? So bottom line here is if we take a look at the graph of the cosine between 0 and pi over 2, that would look essentially something like that. And our issue here is that we're going to put a line in here somewhere so that when we divide this region in two parts, that each part is equal to one another. Okay? So pi over 4 would probably not be a good guess because it would be definitely more area on the left than there would be on the right if we had pi over 4, wouldn't it? So it's probably, if I drew a picture, maybe it's something like that. So bottom line though is that we know the integral from 0 to our c value of cosine x dx has to be equal to c to pi over 2 of our integral of cosine x dx. So ultimately, wouldn't that have to be a true sentence right there? Okay. And if that is a true sentence, then we need to see if we can solve it. So if we do the antiderivative of cosine, we get what? Sine, not negative sine. Evaluated on c and 0, so ultimately we'd have sine of c on this side. Sine of 0 would be 0. And on this side, we'd have sine of x evaluated at pi over 2 in c. So we did sine of pi over 2 minus sine of c. we would ultimately have 1 here. So it'd be 1 minus sine c. And if we added sine c to both sides, we'd have 2 sine c over here equals 1. And ultimately we'd have sine c equals a half then. Ultimately trying to get our c by itself. We're trying to solve for c here. So the key question is, when does the sine equal a half? 5/6. And is it surprising that it's less than pi/4? We expected it to be less than pi/4 just based on sheer area. Okay. So, how we do it? Questions on any part of that one? Okay, next.
34.
34, it says if f is an antiderivative of tangent squared x over x squared plus 1, such that f of 1 is equal to a half, then f of 0 is. And you know, again, one thing we need to start doing here is recognizing that you know, the different types of problems that we had. I mean, we had one like this yesterday where they gave us a function that had an integrand that looked rather daunting, and we may or may not be able to anti-differentiate this, but ultimately, if they give us an initial condition here, and we want to find f of 0, you know, again it says that if f is an antiderivative of this, you know, we can write an antiderivative function by just writing it as an integral function and using the initial condition. Use a different variable here. As such. True. So whether we can integrate it or not, you know, bottom line is if we have this information given, do we even have to bother to try to integrate that? Oh. Matter of fact, what would we be doing if we did try to integrate it? Wasting time. Okay. Don't waste time. Okay. So ultimately, if that's our integral function, because we know an antiderivative for any function is just its integral. Okay. And again, the initial condition is satisfied because we have our 1 here and our half here. So again, since it's a calculator problem, I don't want to waste any time doing let's see. So we need tangent x all squared divided by x squared plus 1. And we're going from 1 to, they wanted f of 0, right?
Yes.
Okay. So we're putting a 0 in there. And with that, if we add a half to it, 0.155, which would be letter B. And that would do it. So again, one thing you want to start recognizing, and it might not be a bad idea for you to even keep some notes about it, is like this problem. Like I said, we had the same problem yesterday. There was really no different. This is a type of problem that at some point you need to say, oh, it's that type. It's easy here. Here's what I do. Get it done. That should be easy points. Okay. Start categorizing things. If this is a category where you just write an integral function, or a category if it's related rates, or whatever the case may be. With a solid of revolution, those are the kind of problems that you want to start keeping track of, whether you're getting them right or wrong on a daily basis. Okay? Because if you continue to get the same kind of problems wrong, those are ones that we want to get some extra help on. But at some point, the different categories of problems that are involved here should be, oh, this is that category. Here we go. Let's do it. Okay? Just make sure we know how to do those steps. Okay. All right. What else? 31, 35. 36 to 40. Let's see, 36 says that this is the local linear approximation of a function f will always be greater than or equal to the function's value if, for all x in the interval containing the point of tangency, the following are true. So let's see if we look at our first part. Says the derivative is less than 0. Okay. So the derivative is less than 0. And again, it says the local linear approximation, which the local linear approximation is just the tangent line, if you will. Okay? And it says that the tangent line approximation is always going to be greater than or equal to the function's value in this interval containing this point of tangency, provided that, and again in this case the derivative is less than 0. So in other words, having a negative derivative, well, let's look at some cases of a negative derivative. If I had a negative derivative, it could look something like that. Okay? And at the point of tangency, would the tangent line be greater than the function? Yeah. But what if it looked like this? So therefore, is this right? The derivative is less than 0, that's always going to be true? No, because there's our counterexample right there. What about part B? The derivative is greater than 0. Well, if the derivative was greater than 0, we could have that situation, which the answer would definitely be no. There's our counterexample. Okay. And if we had, whoops, wrong way. If we had something like that, it would be yes. Okay, bottom line here is these two no's, what do they have in common? Yeah, they're both concave up. Okay. These two, where it was true, are both concave up. They're both concave down. So, see anything that looks like that? Would it be C? Okay. As long as the function's concave down, then the tangent line is going to be above the curve, isn't it? What else? 36 to 40. Mike? 39 says, how many relative extreme values does the function whose derivative is given by the following between have in the interval 0 to 1? So we have our function is, actually it's a derivative function, is sine of ln x. Okay. And ultimately, we want to know how many relative extreme values does the function whose derivative that's given by this have in the interval 0 to 1, including 1, keep in mind. So bottom line here is that if we look at this function, this derivative, we need to know ultimately when does this equal 0. And there's not going to be anywhere it doesn't exist because those are both continuous functions composed. It's another continuous function. So bottom line is we need to know when this is equal to 0, we're going to have possible maximums or minimums. True? So again, it's a calculator problem. So we put that in our y equals sine of ln x. And we go 0 to 1. Got it on negative 3 to 3, so see how that looks here. Alright, so bottom line here is that it appears that the answer is what? In that window, it appears that the answer is, remember, keep in mind that 1 is included here. Yeah, it could possibly be 2 here. It looks like the derivative equals 0 there. It looks like it. I mean, we need to investigate a little further. So it looks like it should be 2. Now, here's where we have to be a little bit careful here, though, is that keeping in mind that the function type that we have here, if I have sine of ln x here, remember ln x, as ln x gets close to 0, okay, in other words, when we're over here, when ln x gets close to 0, the values of, the y values of ln x are going to be infinitely small. It's going to approach negative infinity, isn't it? Okay? And ultimately, what's going to happen when I put numbers like that into the sine function? Well, the sine function does what? Goes up and down and oscillates, doesn't it? Okay? And keep in mind that I'm going to, as I approach 0 here, I'm going to put, an infinite amount of numbers in here that are, going to be getting smaller and smaller. Okay, so what we need to recognize is that we need to investigate this a little closer when we look at our y values here. If we go from between, let's say, 0 and, let's say, 0.1, okay. We'll go by 0.05s, and we go, keep it as that. Alright. Notice that we see a 0 there. And remember in the other window, we go, keep in mind if I look at that point right there, that's 0.05 is my point that I just created there, my other 0. So that was 0.05. If I go back to my original window, which was 0 to 1, question is that the only one that we see there? So let's take a look again at our 0.01 window. Well, actually, let's keep it at that. If I do my 0 command. Okay, we do get that same 0 that we saw in that same window, right? So it looks like that was the right one. And again, over here we could test that one and see that it's also 0. Okay. All right. And if we go, I'll change my window to something even smaller. Okay. Now, if you look at that picture with an even smaller window around 0, if you go 0 command on that one, notice that where are we already? We're already to the left of that 0.05 that we saw, aren't we? So if we find that one, we're going to get that. So there's yet another 0. So far we're at 3 that we found for sure. Right? Okay. And if we change our window to go even smaller, see what happens. And it looks like there's another one coming down there, isn't there? Even closer to 0 yet. Okay.
How is that possible?
So it's possible because your graphing calculator is it's not an infallible tool. It doesn't show you everything. It totally depends on what window you have to see which ones. But bottom line is we can see another one there. We can do the 0 command on that, and it's going to be even less than that 0.002 that we had there. Okay. So, like I said, a lot of people are going to get that wrong because they'd see the 2 and just mark 2 and call it good. Okay. But like I said, with a function like this, there's a little more than meets the eye. I mean, we get a complicated function like that. Think about why there might be more than one answer to this. Okay. As we get closer to 0, because again, if we take these natural log values, and let's say we put in the natural log of 0.1, that's going to give us some value here, sine of whatever natural log of 0.1 is. Okay. And as we get closer and closer to 0, if I do 0.01 and 0.001 and so on, and get closer and closer, okay, ultimately the upshot of that is that the sine function, no matter what numbers we're putting in there, what y values we're getting in there, we're going to be putting in actually larger and larger values. So at some point we're going to be putting in sine, we're going to be putting in -5, let's say, then -10, then -20, then -30, and then -40, and so on. Okay, and so ultimately, how many zeros are there going to be in here? There's essentially going to be an infinite amount of zeros, aren't there? Okay, as we approach 0. Just remember, this right here, as we let x get big, or small I should say, as we get closer to 0, if you will, as we let that get closer to 0, this is going to continue to produce numbers that are more and more negative, -5, -10, negative, and if you want to do it in terms of 0 and 2 pi, something on the way to 0 is going to give us -2 pi, then -4 pi, then -6 pi, then -8 pi, and every time we have a -4 pi, -2 pi, -8 pi, -6 pi, -224 pi, it's going to give us a what? A 0. Fair enough? Alright, so essentially, if a problem looks like it's too easy to be true, then it might be. So just make sure you think about it a little bit before you make a final decision. Alright, what else?
Wait, what other functions would that one cosine do that too?
Yeah.
They have 0.
So it was the same circumstance with cosine? Yeah.
Are there any other trigonometry like that?
Not that I can think of off the top of my head, but bottom line is that's the reason why we're doing this, is you're getting experience seeing functions that might have some possibilities like that. Mike?
40.
On 40 we have a function that is a cubic, so we got f of x equals x cubed minus 7x squared plus 25x minus 39. And they tell us that let g be the inverse function of f, and we want to know what is the value, or what is the value of the inverse, which is g, its derivative at 0. So remember the relationship between functions inverses here. We could certainly try to find g if we wanted to here, but the problem is we'd have to replace the y's with x's and the x's with y's and then solve for y. And if we have this, we have to solve for y. It's going to be very difficult to solve that equation for y. Really impossible for us, especially with the time frame that we'd have. Okay. So bottom line is we need to remember what is the relationship between the derivatives of inverse functions. Okay. So remember what the relationship is that, let's say we have two famous inverses like an exponential and a logarithm like that. Okay. If we have the derivative at this point, okay, then the corresponding point's derivative, let's say this is the point, whatever, 3, 2 or something, then at 2, 3 for this function, okay, the derivatives here would be flips of each other. So if this derivative is d, then this derivative over here is going to be 1 over d. Okay. So the key issue though is finding the corresponding points, if you will. So we need to know something about the derivative of f here because it's going to be related to the derivative of g. So if we did 3x squared minus 14x plus 25, that would be our derivative of f here. Alright, and ultimately we want to know what is the derivative of g at 0. Okay? So keep in mind that the corresponding point then on the g function is 0 something. Okay? So if 0 something is on the g function, then something 0 is the point in question on the f function. So something 0 is our point on the f function. So we need to find that x value first because that x value here is going to be the y value here. All right? And ultimately this x value is going to be what we put into our derivative that we just found. Okay? So the question is, how do we find this x-intercept of this equation? Well, it's a cubic function, so I wouldn't spend any time doing any algebra. I would use the calculator to find that point. So we got our equation here is x cubed minus 7x squared plus 25x minus 39. And it looks like our 0 is, looks like it's 3. I guess if we plug 3 in here, we can see this is going to be 8 minus 63 plus 75. So these two would make 12. And no, that's not going to work. That's not going to work. Yeah, it is 3. How did I do that wrong? No, this is not. No, this is 27. So, yeah, 27 and negative 39 would make negative 12. These two would make positive 12. So yeah, it's 3. Okay. So bottom line is that 3, 0 and 0, 3 are the two corresponding points for these. Because ultimately we want to know when the g's x is 0. Okay? And if the g's x is 0, then the f's y is 0. And that's how we're going to find this x value in question. So bottom line is if we find our point, which is the key issue, making sure we can find the right point here that we're dealing with. Okay? Once we find that point, then if we can find the derivative of f at 3, which ultimately is going to be 27 minus 42, be negative 15, plus 25, be 10. Alright, and so if we know that the f's derivative at 3 is 10, okay, then g's derivative at the corresponding point, which is where the x equals 0 and the y equals 3 instead, okay, is going to be the reciprocal, which is 1/10. Okay. Letter C. Alright, so again, key issue here is that if we have inverse functions, okay, when one has the point AB, the other one contains the point BA. Okay. So we need to make sure we find the right point where the one's x is the other's y, or vice versa. Once we find that point, then we know that the derivatives are related such that at those corresponding points, okay, one's derivative is x, the other's derivative is 1 over x. Anything else up through 40? Okay. 38, so we have a definition of a derivative problem. And again, this is where we want to continue to stress that we need to start seeing these patterns and recognizing that all this is just the definition of a derivative. Okay? Because if we can see that it is the definition of a derivative, then that'll give us the insight as to what to do with it. Okay? So recognizing that this is a difference quotient, we got a y minus y, x minus x situation. Alright, and we know that this derivative is equal to negative 0.628, it says. Alright, and it says that if this limit is equal to negative 0.628, then near the point x equals 3, the graph of g is what? Well, again, this is the derivative of our g function at 3. So what could be said then, if this derivative is negative, then this function would have to be what? Have to be decreasing. So again, in the scheme of things, as long as you recognize that that's the derivative of g, then it's a pretty easy problem, isn't it? Okay. So again, these are the kind of patterns we need to start recognizing when we see that, because like I said, on the AP test, that problem should take you less than 5 seconds, right? And you got time to deal with, make sure we're spending our time wisely.
How long do you have per problem?
On the calculator part, you get 50 minutes for 17 problems. So again, that's why when we get done here with our in-class multiple choice here, keep in mind that we won't have this whole book finished. So there's lots of problems you can practice on your own too. So and I have all the answers if you want to look at them. So like I said, the more experience you have seeing these types of problems, and the easier chance you're gonna have when you see it on the test to know what to do with it. What else? Last part, 41 to 45. 43, we have a piecewise function given, and it's e to the negative x plus 2 for x less than 0, that is, and then ax plus b for x greater than or equal to 0. And the issue here is that we want to find that a and b are constants, and it says f is differentiable at 0. Then what is the value of a plus b? So keep in mind, if it's differentiable at 0, okay, two issues have to be satisfied here. Number one, if it's differentiable at 0, we know this e to the negative x plus 2 function. We know that e to the 0 here would be 1, and if I have a plus 2, that means that'd be right there. So ultimately, thinking of the curve, we'd have something like that coming down there. Okay. And ultimately, it's going to go into this line. Well, this line is going to have to, essentially, it's going to have to be essentially an extension of that, which means it's going to have to not only cross the x-axis at that same y-axis at that same point, okay, but it also has to have the same what going through there? Same slope. Okay. So already we know the answer to B. It's 3, isn't it? True? And then ultimately we just need to know the slope that A has to be, and if we find the slope of our curve here, we can do that. So the slope of our curve is going to be the derivative of our curve, which is itself times the derivative of the argument, plus 2, or not plus 2, plus 0. So the 2 part would be a 0. So ultimately it's just going to be negative e to the negative x is our derivative. Okay. And if I put a 0 in there, I'm going to get negative e to the 0, be ultimately negative 1. And just picture-wise, does it make common sense that negative 1 would be reasonable there? Decreasing through there? Alright, so that means my equation for that line then is negative 1x plus 3, which ultimately the value of a plus b would be 2. What else? Mike? 1. Okay, we got on 41 says the expression we have 4, then 0 to 2 of rho x dx. This gives the number of people living on one side of a 4-mile long stretch of a highway, where x is the number of miles from the highway, and we want to know what are the units of p of x. Okay. So ultimately the expression again says it gives the number of people living on one side of a 4-mile long stretch of highway, and it says that x is the number of miles from the highway. So let's think about what this would have to be, right, in terms of this row x function. So whatever it looked like, say it looked like that, whatever, it's some shape, right? And we know that x, the independent variable of this row x function, is measured in miles. True? And we ultimately know that this integral is measured in people. True? It says it gives the number of people, etc. The units are people. So bottom line here is that if this is our row x function, then what is the independent variable going to have to be measured in over here in order to give us a multiplication? Remember, when we find area under a curve, we multiply the two units together. So what is this going to have to be in order to multiply it by miles and get people? Wouldn't it be people per mile? Because if I did people per mile times miles, I'd get what? I'd get exactly what I have there, which is people. So therefore, yeah, it should actually be. Oh, I know why. Keep in mind that there's a 4 out in front of here. There's a 4-mile stretch of highway here. Okay. So the units on this are actually, it's going to be people times 4, and 4 is in what? 4 is in miles. So actually, that multiplying that by 4 makes it have another miles on here. And ultimately, how could we get rid of another miles? Have this be people what? People per square mile. Yeah, you got to factor in that 4 part out in front. I didn't see that 4 out there. That 4 counts for the fact that this is over a 4-mile stretch. So when we multiply by 4, we're doing this for 4 miles, so that miles has to be factored in also. Okay. Right. Ultimately, if it were just people per mile here, then it would be people times miles, and we don't want it to be miles people. We want it to be people. Okay. So that 4, we can get rid of that by making the units on this be miles squared on the bottom. Alright. Well, this one would be people per mile, but remember we still have another miles over here, so there's essentially another miles that we've multiplied here. Remember there's an extra miles over here with the 4. This is ultimately miles, and we want the whole thing to be people. And right now it would be miles people if we just did it as such. We need to get rid of that other miles.
But isn't the answer people per mile? So didn't you already
People
get
per mile
first
squared.
miles?
The answer for this part here, which is what we're looking for, is people per mile squared.
So you get rid of all the miles.
Yeah. So like I said, if we just made this right here people per mile only, we'd have people per mile times miles, which would be people. But then that 4 would still be there with another miles. We don't want people miles, we want people. Okay. So if we made this people per mile squared, then the area part would be people per mile times another miles would get us to people. That's what we want.
I see what you're saying.
Like,
What's the unit of, I mean, the x part is not mile because it's not a function.
well, the independent variable here, x, is the number of miles from the highway. Okay. So this p of x function needs to represent something in terms of miles. I mean, the x is the independent variable here is miles. Okay.
No, it asks what's the unit of the x. So
Right. The unit of p of x, though, is going to be whatever on the y-axis over here. Okay. They want the units of p of x.
The y.
Okay. In other words, what is the y measured in? Because like if I made an xy chart for this, if I made xy and this is our p of x function, again, this would be in miles. and this is going to be in something. We need to figure out what that something is, and in this case, it needs to be people per square mile. Because ultimately, again, in multiplying just to get the area under the P curve, if we just did the area only, which would be that without the 4, okay, then we'd need, if we did this times this, okay, if that 4 wasn't there, this could just be people per mile times miles and give us people. Okay? But since the 4 is there, we've multiplied the integral by another set of miles. So really we have another miles to get rid of. So the only way that can happen is if we make this people per mile squared. Because 1 miles would be gotten rid of by doing the multiplication here with the integration part, and then we can get rid of the other miles here by doing the other multiplication. Okay. So ultimately, again, this is just the unit on our y-coordinate, which is the units of row x, if you will. Good one. What else? Go.
42.
On 42, we got a circle or a rectangle inscribed in a semicircle. Has radius 8 and lying on one side of the diameter. So essentially we have that situation. So a maximum possible area for that rectangle. Remember to maximize an area, you need to first write the equation first. In terms of x, this would be 2x for the length. We draw it in a coordinate plane like all the other ones that we've done. And then the width here is going to be whatever the function is. Well, if this is a circle with a radius of 8 here, this is going to be y equals the square root of 64 minus x squared. Would be the function that is the top of this circle. And so therefore we'd have the square root of 64 minus x squared here. Alright. So with that, that would be our area function. Give us the area of that rectangle at any particular x. And then from there, we need to find the derivative and set it equal to 0. Maximize it. So we have a product situation here. So if we did our 2x first times the, if I write this as 64 minus x squared to the 1/2, I can treat it as a power function. I'd have 1/2, 64 minus x squared to the negative 1/2 times negative 2x. That would be the first part of our product rule. Plus square root of 64 minus x squared times 2, the derivative of the first. Alright, so, and trying to get all that stuff together here, we'd have the half and the 2 could cancel out, still have another 2 over here, so we'd have negative 2x on top, square root of 64 minus x squared on the bottom, plus 2 over, square root of 60, no, not 2 over, but 2 times, I should say, 64 minus x squared. Alright. Doesn't have the negative power on it. So, again, these two, this and this, would make negative 4x squared, but we have a half there, so negative 2. Actually, there's a square there too. So negative 2x squared, that is. And on the bottom, we put our square root. And we need to set this equal to 0, so the best way to do that would be to get a common denominator and make one fraction out of this. Obviously, the common denominator would be this. So we'd have negative 2x squared plus, if we multiplied the top by that, we'd have 64 minus x squared. On the bottom, we would have square root of 64 minus x squared. Alright. And ultimately, if this is going to equal 0, then what part of that fraction needs to equal 0? Top does. And if we put stuff together here, we're going to get negative 4x squared plus 128 on the top. We distribute that too, combine like terms. And if we set that equal to 0, we divide here. 128 divided by 4 is going to be 128 divided by 2 would be 64. Divided by 2 again would be 32. So we get x equals square root of 32. We can simplify that later. All we want here is the maximum area though. So ultimately that's going to have to go where? Into our area function, which was this. So we got 2 square root of 32. And then in the parentheses I'd add square root of 32 again. So I'm going to put a square root of 32 into here and get 32. 64 minus 32 would be 32. And so those two multiplied together would give me 32. So 2 times 32 would be 64. And that would do it. So again, key calculus information here. I mean, most of getting that right is algebra, but bottom line is, in the calculus situation, you just need to recognize that if we're trying to maximize anything, okay, we can write an equation for it in one variable. Okay, then once we write that equation, we can find the derivative, set it equal to 0, solve said problem.
From the beginning, when you were finding length, how did you know that's 2x?
Well, the way I have it drawn with the origin in the middle of this circle, right? In order to be able to use this as my function. I don't want to put it anywhere else on the plane because then this wouldn't be the right equation for it.
How come the length just could be x?
Well, because ultimately, if I let it be x, x this way and x that way, if I go, if the dimensions of this thing, if I go from 0 to here, isn't that x? And if I go 0 to here, that ultimately would be negative x. Right? So what's the actual length of the rectangle? X in both directions, so it'd be 2x. I suppose if you wanted to call the whole thing x, you could probably manipulate this, and then when you get done, still wind up with the same answer. Since every problem we've done like this, we've used x on one side, x on the other, I would just continue to do it that way. It's easier to deal with. What else? 31 to 45. On 45 says the line y equals mx plus b. B greater than or equal to 2 is tangent to the graph of this parabola at a point in the first quadrant. And it says, what are the possible values of b? So, keeping in mind that, again, we have this parabola. It's in standard form here. The vertex is going to be at 2, 2. And if we go ahead and graph that, whoops, I forget my squared. So that doesn't look like a parabola. There we go. Alright, so it looks like 1 is a 0 and 3 is a 0 also. Alright, now the stipulation here is that in our equation here, b has to be greater than or equal to 2, it says. So that means we could have a y-intercept at 2, possibly. And it says, what are the possible values of b, knowing that this line here is tangent to this graph at a point in the first quadrant? Well, ultimately, if we drew that line and had it be equal to 2, would that be reasonable to have it be a tangent line? Since the vertex is at 2, 2, that would be more than reasonable, wouldn't it? Okay. So 2 could be a possibility. So 2 could be our y-intercept here. What if we drew it at somewhere above it, like here? Could it be possible to hit that curve at one point? Could be, sure. All right. And then the bottom line here, I guess, is this. If I were to continue to go a little bit higher and a little bit higher with my tangent lines, okay, what's eventually going to happen? Eventually, we could draw a tangent line way up here, but the tangent line might be where? Not in the first quadrant, but in the fourth. Okay. Could be in the fourth quadrant, isn't it? So the bottom line is, how high can we go and still be in the first quadrant is what the issue is, right? And looking at our choices here, it looks like our choices are 10, 12, 14, or 20. Right? So let's see about, let's see if we made it 10. If we said y equals, and our, actually, if we did mx plus 10 for argument's sake here, alright? Because the issue then, if we have that be 10, okay, what would our slope be? Well, let's think about this. So we know that the equation here is y equals negative 2 x minus 2 squared plus 2. Okay, keep in mind that the slope that we use here for our line is going to have the same derivative that we have at our point in question. Okay, so if we look at our derivative here, we'd have negative 4 x minus 2 as our derivative. So ultimately negative 4x plus 8. would be the derivative of said function. Alright, so this would be the derivative of our curve that we have here. Alright, and so if we took, we know that at 2 is our point where we have the vertex here, so it needs to be beyond 2 somewhere. So let's say we go to 3, and really, wouldn't 3 be the last x value possible to still be in the first quadrant? Anything beyond an x value of 3, it's not going to work, is it? Because if it's beyond the next value of 3, we're in the fourth quadrant. So let's see, if we put a 3 in there, we're going to get negative 4 as our slope. We're going to get negative 12 plus 8. Alright, so negative 4 is the slope at 3. And if that's the slope at 3, keeping in mind that this is kind of like our boundary point here, we can't go any further than this. Bottom line is if we drew that tangent line there, we just need to see when is that going to cross the x-axis. And again, my picture's not very good, but bottom line is if I were to draw a tangent line at that last possible point, right, if I could find the y-intercept of that, then I would have my answer, wouldn't I? So bottom line here is the question is then if I had my slope here of my line in question be y equals negative 4x plus b, and this way I don't even have to test 10 and see if it works. We can just find b directly. So keep in mind that we know that the slope here has to be negative 4 for our ultimately last possible line that's going to work here. And how can we find this b? Well, what do we know about x and y here? Okay. What point does this line have to go to? It's got to go through 3, 0, doesn't it? So if I put a 0 in here and a 3 in here, I could just solve for b and get 12, couldn't I? So if I get 12 equals b, and ultimately that makes our answer choice C. 12 is the highest it could go. Alright. Again, key issue is that this is the last possible tangent line that could be drawn would be at x equals 3, because anything beyond 3 would be in the fourth quadrant in terms of the point of tangency. Okay. So we can calculate the derivative at 3 here, so we can find our slope of our tangent line, because we know the derivative, and we can put 3 in there easily enough. Okay. And then bottom line is this line that I've drawn here. Okay. If we can write the equation for it, then we can find the y-intercept, can't we? And like I said, and we know that anything that's steeper than that, anything that would be up here, anything higher than 12, it's going to, hit this curve, but it's not going to hit it until we're in the fourth quadrant. What else? Um, 44, we have, says silt is being dredged out of a river bed at a rate of R of t at 100, 5t squared minus t minus 1 on top, 5t squared plus t on the bottom. And this is in gallons per minute, keep that in mind. As soon as you see a rate function, pretty likely going to be an integral question. Okay. And ultimately it says approximately how much silt is dredged from the riverbed between time 2 and time 10. Well, all it is just an integral of that function then, isn't it? And it's a calculator problem, so don't waste any time trying to find an antiderivative for that, right? Should turn out to be C, 731. Okay. Hey, we're going to do a quiz tomorrow. We're going to have some multiple choice questions on the quiz.